Fine. So the net entropy change has been positive. So the process is spontaneous. Now we don't have to give out the reasons that this is giving out energy, that air molecules is gaining kinetic energy, and there are many molecules around here, so the kinetic energy is getting more dispersed out. So we don't have to talk in terms of that abstract. We can talk more concretely in terms of these mathematical formulas and numbers. Now this is going to be a positive number, and we can show that to anyone. Look, this is positive number, so the process is spontaneous. That gives a greater advantage for analysis of this kind of situation. If you try to think of the other way around, suppose you are going this way. Suppose you have a ice at 300 degree Kelvin at room temperature. You have a tea or a coffee, and you're trying to make it hot, and it becomes hot on itself automatically, spontaneously, without any external assistance. Now let's see if that is possible, having faith in this equation. Now suppose, if we have to see the change in entropy of the cup. Now suppose it has gained 100 joule of heat this time. So if 100 joule of heat has been gained on an average, the temperature because from 300 to ongoing from 373, the temperature will continuously change. But for convenience of analysis, I'm taking it as 373 Kelvin. This is the entropy change. Because it is gaining heat, so ds will be positive and the whole entropy change will be positive. And because surrounding is giving out heat, so the dq for surrounding is negative. And I'm taking the temperature of surrounding as constant because temperature of surrounding won't change much. So this time you can see that this fraction, this denominator is smaller, so this fraction is going to be larger. And that's negative. So the whole sum is going to come out as negative. So this process is not possible because change in entropy is negative. Fine. So this seems to work, and this is important. So quickly learn this. This is the first formula that we have studied in entropy in the second law of thermodynamics, that change in entropy is dq reversible by T. But you are not having you're not comfortable with why this dq is dq reversible. I've given you a reason. We'll see one more reason in the next topic that we are going to study. But for time being, let me quickly summarize what we have studied. We tried to understand in which direction a particular process will move, in which direction it will be spontaneous. Then looking at various observations, we established that a process is spontaneous when there is diffusion of energy. Now we tried to find a mathematical formula, a mathematical physical quantity that will tell us whether energy is being diffused or not. And that mathematical or physical function, quantity, I have defined as entropy, and entropy gives us the idea about how much energy is being spread out. It gives us an idea of the diffusion of energy, and it is defined as dq reversible by T. That much we have done. Okay, so now let's start to develop a mathematical form of thermodynamics second law. The expression that I told you before, that ds is equal to dq by T, dq reversible by T. Now this has been derived from Carnot cycle. Carnot cycle is a cycle of heat engine. We'll see what heat engine is and what those cycles are. But from Carnot cycle, this expression has been derived historically. Clashes did it. So it's very important for us to look at the Carnot cycle, and once we look at the result of Carnot cycle, then we will realize that actually there has to be a quantity defined like dq reversible by T, and that quantity was named as entropy by clashes. So this ds actually becomes dq reversible by T. So for the time being, let's forget what entropy is and what we're doing. Let's lay that at rest for some time, and let's begin a fresh thing, and then we'll relate to what the result will come out from this topic to what we have been doing previously. So we are going to study a heat engine, and that heat engine is called the cycle on which that heat engine runs. That cycle is called Carnot cycle. What happens in any heat engine is there's a source from which a fuel a fuel takes up the heat and becomes hot. Suppose that source of heat is at TH and we are considering that the temperature is constant. So this is constant as at TH. Now from here, Q amount of heat is given into the fuel. That fuel goes into the engine. That engine does some work. Now this work is never going to be equal to QH, because if all the amount of energy provided is converted into work, then the efficiency of the engine would be 100%. By our observation, no engine has 100% efficiency. So this Q is a fraction. This W is a fraction of the total amount of heat that was given to the engine. The rest of them comes out of the engine as exhaust. So this exhaust energy is given to this sink, and this sink is at lower temperature. Let's call it as TC. Fine. Now this amount of energy given to the sink is QC. Fine. So it takes QH, gives out energy W, does the work W, and the exhaust energy, the exhaust heat is QC. That's what the engine does. Now what happens, suppose you have a fuel, it takes energy, does some work, moves a turbine or whatever inside the engine. We don't have to look into the details of the construction of this engine. And W amount of work is done and QC amount of heat is given out. Now this QC, the fuel, whichever is in this engine, that is cooled down, and again that is the same fuel is pumped into the sink, and that fuel abstracts energy from the source, not sink, and then that it again becomes hot and it again expands, again turns the turbine, does some work, again is sent to the sink, cools down, again is sent to the source, it gets heated up, expands, turns the turbine, and then comes down. So it's a cyclic process. Fine. So this cyclic process can take place by various means, and one of the mean is via Carnot cycle. What happens in a Carnot cycle is you start from a position, from a state, you move on from state 1 to state 2. Now this is a hyperbolic curve, and if this is pressure and this is volume, we understand then that isothermal processes are hyperbolic. So I intend to draw a hyperbola. That means I intend to work out a isothermal process. So I'm going from 1 to 2. Now this process which I am carrying out, which is a Carnot cycle. So I'm telling you what a Carnot cycle is. What a Carnot cycle is, you start from a state 1, you move on to state 2, and this is a reversible isothermal process. Okay, from state 2 you go on to state 3, and this is reversible adiabatic process. Fine. You come down to state 3. Now from 1 to 2 and from 2 to 3 you are having expansion because volume is increasing, and because the whole engine runs in a cyclic process, so you have to come back somehow to state 1. Only then the whole cycle would be completed, and for coming back you have to go for compression. So the first compression is again the same as this, reversible isothermal, and the second compression is again the same as this, reversible adiabatic. So you start from 1, then 2, then 3, and then 4. One question that could arise in your mind is why we are taking it such that it's a isothermal and then adiabatic and again isothermal and then again adiabatic. One obvious reason is if I do it this way, then I can reach back to 1. If I carry out isothermal process and then adiabatic reversible process and then isothermal and then adiabatic, then I can get a cyclic process like this.